Hello friends, I am Santosh Babanrao Gaikwad, working as an assistant professor, Department of Chemistry, at Pondlikara Gauri Arts and Science College, Shirpurjan, District, Washing. In previous lecture, we have started to study most important organic compound containing carbonyl group in their functional groups. In previous lecture, we studied synthesis of aldehydes. With this, we covered topic like nomenclature of aldehydes, molecular orbital structure of it, as well as its polarity and some synthetic approach with their probable reaction mechanism. In this lecture, we are going to study most important synthetic method for the synthesis of ketones. With this, we also overlook on nomenclature of ketones. So, watch this video to the end. Before we start the lecture, we are going to know about ketones. Then, what is the ketone and what is the chemical formula of the ketones? In ketones, carbonyl carbon attached to the two same or different alkyl or aryl groups. This we can see in its molecular structure, that is RCOR, where R and R dash are any alkyl or aryl substituent which are attached to carbonyl groups. Ketones are classified into two categories. First is a symmetrical ketones, where carbonyl group is directly attached to the same two alkyl or aryl substituents. For example, here we can see acetone, where two methyl groups attached to the carbonyl group. Next is a unsymmetrical ketones, where carbonyl group is directly attached to the two different alkyl or aryl substituents. For example, here we can see unsymmetrical ketones is acetophenone, where carbonyl group is attached to the one side to the methyl group and other side to the phenyl group. Both groups are different. In addition to this topic, we can say that aldehydes, ketones and carboxylic acids are widespread in plant and animal kingdom. They play an important role in biological processes of life. They add fragrance and flavor to nature. For example, vanillin in nature, we can find it in vanilla beans. Next is salicylaldehyde. We can extract it from meadowsweet. And next is a cinnamaldehyde. We can extract it from cinnamon, which have very pleasant fragrances. They are used in many food industries, that is aldehyde, ketones and carboxylic acids are used in many food industries and pharmaceuticals to add flavors. Some of these families are manufactured for the use as a solvent like acetone and for preparing materials like adhesives, paints, resins, perfumes, plastics, fabrics, etc. Now we study nomenclature of ketone. Nomenclature of any organic compound is done with the two type naming system, that is first is a common name system and the second is IUPAC nomenclature system, which is universally accepted and applied. Hence, first we study nomenclature of ketone by common name system. Ketones are often called by their common names instead of IUPAC names. The common names of ketones are derived by naming two alkyl or aryl groups bonded to the carbonyl groups. Some ketones have historical common names. For example, the simplest ketone is a dimethyl ketone, that is acetone. And other example is ethyl methyl ketone. The location of substituents are indicated by Greek letters alpha and alpha dash, beta and beta dash, and so on, beginning with the carbon atom next to the carbonyl group indicated as alpha alpha dash, and so on. For example, beta bromomethyl propyl ketone, where bromide substituent is attached to the beta position to the carbonyl group of ethyl methyl ketone. ethyl propyl ketones. For aryl system, alkyl phenyl ketones are usually named adding the acyl group as a prefix to phenone. For example, acetophenone. The common name in aryl system is depends on the substituent attached to ortho, meta and para position, which we can see here. For example, para hydroxyacetophenone, where hydroxy group is attached to the para position of ketone. Now we are going to study IUPAC nomenclature for ketone. This nomenclature system is universally accepted and applied. The IUPAC name of open chain aliphatic ketones are derived from the name of corresponding alkane by removing or replacing the ending E of alkane with ONE or ONE. In case of ketones, the numbering begins from the end nearer to the carbonyl group. For example, here propane to 1, and next example for aliphatic simple ketone is butane to 1. The substituents are prefixed in alphabetical order along with the numericals indicating their positions in the carbon chain. For example, here 4-bromopentane to 1. The name of the simplest aromatic ketone carrying an acetyl group on the benzene ring is 1-phenylethane 1-one. However, the common name acetophenone is also accepted by the IUPAC. Another example for aromatic ketone is 1,4-hydroxy propane 1-one, where carbonyl group is always considered as at position number 1. Hydroxyl group attached to 4 position carbon to the carbonyl functional group on benzene ring. Now we are moving to our most important part of this lecture. We are going to study some synthetic methods for the synthesis of ketones. Here we take reactions for our simplicity. We may change alkyl or aryl groups attached to carbonyl groups in ketones. We start with the first synthesis of acetone by oxidation of isopropanol. In this reaction, when isopropanol is oxidized in presence of acidified solution of potassium dichromate under the controlled condition to prevent further oxidation to carboxylic acid, this gives acetone. Similar oxidation reaction can be performed with different reagents, which we can see here. First, we have seen in this reaction, and the second reagent for the conversion of isopropanol to acetone is alkaline potassium permanganate. Third reagent is chromium trioxide in acetic acid, where we get acetone from isopropanol. We do not go for further possible reaction mechanism of this reaction. Just follow the link of my previous lecture of synthesis of acetaldehyde or aldehyde for the exact same probable mechanism which is given in description box. Now we study next synthetic method for the synthesis of acetone by hydrolysis of 2,2-dichloropropane. In this reaction, 2,2-dichloropropane on alkaline hydrolysis in presence of sodium hydroxide gives an unstable geminal diol which easily loses water molecule and produce acetone. We can see here. In its probable reaction mechanism, hydroxyl group of sodium hydroxide attacks on electron deficient carbon atom with the removal of one of the chloride from the 2,2-dichloropropane. Again, another molecule of sodium hydroxide reacts as like before and forms geminal diol. This is very unstable intermediate and converts into acetone with the loss of water molecule. The next synthetic method for the preparation of acetone by hydration of propane, that is alkyne or other than ethine, because ethine on hydration gives acetaldehyde. We have seen in previous lecture. Acetone can be prepared by addition of propane through 30% of sulfuric acid containing 1% of mercuric sulfate. It forms unstable enol, gives acetone. And the possible reaction mechanism of this reaction, water molecule adds to the propane to form unstable enol intermediate, which tautomerize into ketoenol form. Finally, after the proton transfer, formation of acetone takes place. Here we completed synthetic reactions of acetone, or here we can say aliphatic ketones. Now we study some synthetic methods for the synthesis of acetophenone or any substituted aryl system. We start with the first synthetic method for the synthesis of acetophenone by acylation of benzene. This reaction is also known as Friedel-Craft Acylation reaction. In this reaction, benzene on acylation with acetic anhydride or acyl halide in presence of aluminum chloride. This gives our product acetophenone. Now we take overlook on easiest possible reaction mechanism of this reaction, or Friedel-Craft acylation reaction. In this reaction, acyl halide reacts with, or acetic anhydride reacts with the Lewis acid to form complex. In the next step, loss of halide to the Lewis acid forms electrophilic acylium ion, which is positively charged with electron deficient carbon center or carbon positively centered. In the next step, the p electron of aromatic carbon-carbon double bond acts as a nucleophile in benzene, attacking the electrophilic carbon atom of acylium ion. This step destroys the aromaticity of benzene, giving the cyclohexadienal cation intermediate, which you can see here. This is a slow step. In the last step, removal of proton from the sp3 carbon containing acyl group reforms the carbon-carbon double bond and the aromatic system of benzene system with generating HCl and regenerating aluminum chloride. This forms our target molecule, that is acetophenone. Now we study next synthetic method for the synthesis of acetophenone by reduction of acetonitrile using Grignard reagent. In this reaction, phenyl magnesium bromide reacts with the acetonitrile in dry ether, gives addition complex, which on acid hydrolysis with dilute sulfuric acid or dilute hydrochloric acid gives our product acetophenone. Now we can see the probable reaction mechanism of this reaction. In the first step, the nucleophilic carbon in the organometallic reagent, that is phenyl magnesium bromide, adds to the electrophilic carbon in the polar nitrile group. Electron from the cyanide moves to the electronegative nitrogen, creating an intermediate imine salt complex. In the next step, on acid hydrolysis, intermediate salt protonates gives the imine. Further, on acid hydrolysis, imines undergo nucleophilic addition, but it requires activation by protonation. Now the nucleophilic oxygen of water molecule attacks the electrophilic carbon of imine with the pi bond breaking to neutralize the change on the nitrogen. Again, in the next step of acid hydrolysis, deprotonation of oxygen from the water molecule to neutralize the positive charge. Before the nitrogen atom or nitrogen system leaves, it needs to made it into better living group by protonation. Finally, with the release of ammonia molecule, formation of acetophenone takes place. Acid or base hydrolysis is the most important step in this reaction of formation of ketone. Without this step, conversion of imine complex to product formation doesn't take place. Now we study last synthetic method for the preparation of acetophenone from acyl chloride in Grignard reagent and cadmium chloride. In this reaction, we are going to study most important reaction, that is transmetallation reaction between Grignard reagent and cadmium chloride. What is transmetallation reaction? In this type of reaction, metal exchange takes place in organometal compounds. In this reaction, acyl chloride reacts with Grignard reagent and cadmium chloride in dry ether, gives our required product, that is acetophenone, which we can see here. Now we take overlook on possible reaction mechanism of this reaction. Mechanism start with the reaction performed within Grignard reagent and cadmium chloride by nucleophilic addition. Here is the loss of chloride ion takes place. This reaction is also transmetallation reaction we discussed before. In this reaction, organocadmium compound is formed. In the next step, organocadmium compound reacts with acyl chloride. It gives acetophenone, which we can see here. Here we completed synthetic methods for the synthesis of aldehyde in previous lecture and synthesis of ketones in this lecture. In next lecture, we continue chemical reactions of aldehyde and ketones. So, see you soon in next lecture. With this, we conclude our today's lecture here. I think all of you satisfied with this knowledge. If any query about this content, comment me in comment box. If you like this video, press like button and don't forget to subscribe here. Also click on bell icon for the notification of my new video. Thank you very much for watching this video.